Hello and welcome to a new video. My name is Herwig and today we will be discussing some community questions I've collected over the past month. We will discuss how to improve the comparative tracking index of thermoplastics. We will discuss laser welding. We will have a look at flame retardant classifications and also carbon neutral plastics and how to achieve carbon neutral plastics. Okay, let us start with the first question, and it was what are the ways to increase comparative tracking index CTI of thermoplastics. So in general, there are polymers which are more likely to form a conducting carbonized path compared to other polymers. So when you think of aliphatic and semi-aromatic polymers, polyamides, polyolefins, fluoropolymers, and also polyesters, they show a high resistance to form a conductive carbonized path. When you take a PPS, polyphenylene sulfide, it is more likely to form a conducting carbonized path, and this together with a low tracking resistance. And when we talk about CTI, it's important the two standards, the IEC 60112 and the UL 746, which are used in several industries to rank the CTI of different polymers. And this I have shown here in the table. So we have the insulating group and then the CTI values from below 100 volts and above 600 and everything in between. And there we see typical materials like in the highest class above 600 volts. We have the polyolefins, polyamides, fluoropolymers, followed by polyesters, polycarbonate, and down here PPS, and in the lower range PEEK, polyamide, and so on. Okay, so how I can improve when I have, for example, PPS, how I can make this better to achieve higher values, which has then advantage in the design of my bus bar or other components. So one way is to use a mineral flame retardant, for example, by adding 8% of a mineral flame retardant to a PPT, the CTI could be increased 13%. And when you ask now what mineral flame retardant I can use, for example, the Actilox 200SN from Nabaltec. Other way is to use additives. So there are multifunctional polyester modified siloxane additives which can be used to improve the CTI. And here's an example from Evonik, the Tecomer HSI. Or the strategy can be to blend with a high CTI polymer. So when we take again PPS, when I add now a polyamide, I can improve the CTI value from 175 volts to 275 volts. Looking at the PPS with 48% glass fiber and polyamide. Here's the example, the Retardant XK2430, for example. Okay, so let us continue with the second question. What should be the minimum transparency level required for plastic laser welding? So in general, thermoplastic transmit in a near infrared beam. So the upper plastics layer needs to have a transparency for wavelengths between 808 nanometers and 1064 nanometers roughly, and a minimum transmission rate of 5% is required. However, optimal would be 30% and greater. So this is also what I've shown here in this graph. So that means in an optimal application case, 30% of the laser energy passes through the transparent upper layer and is absorbed by the lower layer. And when we have additives, fillers, pigments, and part thickness, those are all factors which can negatively influence the transmissivity of your upper layer. Therefore, a careful polymer material selection for laser welding is needed. Okay, let's continue with the third question. It's about flame retardants and flame retardant classification, because we want to shed some light into the standard ISO 1043 section 4 and what are they mean in detail. So here's an example, polyethylene low density, so PELD FR flame retardant, and then we have in brackets 30 plus 40. Now we want to know what is behind that, because it can be that certain applications it's not good to have certain flame retardants due to side reactions like corrosion and so on. And for that we need to have a look in this ISO 1043-4. And this is what we do here. I have here extract starting from the number 10 up to 80. And when you think back now in our example 30 and 40, so 30 are flame retardants based on nitrogen compounds and 40 are flame retardant based on halogen-free organophosphorus compounds. So those is a combined class of flame retardant. So it's not unusual to combine different classes to have better effects in your final compound. And there you see it starts with 10. This can be halogen compounds, and then we have also 50 inorganic phosphorus compounds, 60 is the metal oxides, 70 boron and zinc compounds. Everything above 75 is silicon compounds, and also graphite is used as a flame retardant. So there are more classified, but these are in plastics the most used. And for example, in case you want to overmold copper, like in a bus bar application with a polyamide, which needs to have a certain flame retardant level, attention should be given to use flame retardants from classification 40. So the halogen-free organophosphorus compounds, so organic system, because such flame retardants do not create electrical corrosion on your part, which in turn can result then in a short circuit of the whole system. And yeah, when you think of market segments such as automotive, more and more flame retardant materials in combination with other properties like thermal conductivity and electrical insulation are used. Okay, let's continue with the fourth question. So how to turn thermoplastics carbon neutral or even carbon negative. And a simple answer, yes, it is possible by using specific fillers which are able to lock in more carbon dioxide than they release in a later stage. And here I brought one example, it's biochar. So when you think of forest and wood in general, it's really good material because it's really is in this CO2 balance neutral. And there is a research group around Seth Kane, and his team demonstrated that carbon neutral composite materials can be produced by adding biochar to your polymer. And they made a cradle-to-gate life cycle assessment, and they added the biochar as a filler to HDPE. Virgin version, and also a recycled high-density polyethylene, and also bio-based PLA, so polylactic acid, and also PHB, polyhydroxybutyrate. And when you think of biochar fillers lock carbon in a stable form, and this in a permanent way. So what are the key results of this study? They found out that 40 weight% biochar filler is sufficient enough for recycled HDPE to reach 0 kg CO2 equivalent. With PLA you need a bit more, 50 weight% to reach this 0 kg CO2, and with HDPE, so with virgin material, you're around 52 weight% you need to reach the carbon neutrality. What else they found out? They found out that biochar increases the tensile strength of recycled HDPE by 45% and also stiffness by 126%. So it's also a good mechanical reinforcement filler. And also the flexural storage modulus could be improved by 79%. However, also you have to consider that the whole compound itself got more brittle. So, and also they concluded that adding biochar linearly reduced the global warming potential of the exam plastics by up to 3.3 kg CO2 equivalent per kilo of material compound, which is really great. So this is one example. There are other natural based filler like hemp, which have the same effect, which you can also add and make a carbon neutral material. Okay, so with that I want to close our little community question and answering session. I think there were some really interesting 4 topics we discussed, and I would like to thank you for watching and looking forward to next time. Bye.